Good morning, everyone. Thank you for joining us today. Welcome to our conference call on Apache MADlib. We'll be covering the features in the new 1.15 release. I'm Bob Glithrow, Product Marketing Manager at Pivotal, and we're joined today by Frank McQuillan and Jingyi from Pivotal as well. As a reminder, this call will be recorded and posted to the Greenplum database YouTube channel at the end. I will send out a note to the community when that recording is ready. And if there are any questions, I would ask that you put them in the chat window so that the presenters can address them. And with that said, I'd like to turn it over to Frank to start us today. Thank you.
Thanks, Bob. Yeah, so my name is Frank McQuillan. I work on Apache MADlib. And what we'd like to do, Jingyi and myself, is cover the following topics. First of all, review the 115 release, and then focus on 3 or 4 of the main features in that release and give examples of them, and then look ahead to the next release. So before I start, Bob, can you tell me if I'm coming through clearly? Can you hear me okay?
Yes, Frank, you're coming through just fine.
Okay, great. So let's look at the 115 release to start with. So you can look at the detailed release notes, but this is a description of the high-level features of this release. First of all, we added 3 new algorithms in the utilities area. One is columns to vector, vector to columns, and drop columns, and the other is drop columns. And we'll give demos of these shortly. We also made significant improvements to existing algorithms. For example, in the area of neural networks, we added momentum methods to our multi-layer perceptron. We added correlation, for correlation and covariance, we added grouping support. And the idea behind grouping is it allows you to specify a grouping column in a table and then to run correlation separately on each of those groups. So that saves you having to write additional code to do looping around groups. You can just specify it as a parameter. In the area of decision trees and random forest, we've done some work in variable importance. One, we've added a new kind of variable importance called Impurity variable importance. And we've also added a helper function that makes it easier to display the variable importance against the particular algorithms, the particular, like against the variable important values by variable. We made improvements to the MADlib install and upgrade tool to make it more reliable, and done a number of infrastructure and testing improvements. So at this time, maybe I'll turn it over to Jingyi so she can give us an update on the impurity importance related work that we've done.
Okay, thanks, Frank. I'm going to share my screen. So can everyone see it?
Yes, I can see it.
Sure. So hi, I'm Jingyi, and I also work on MADlib from Pivotal. And today I'm going to introduce the new features we make for both decision tree and random forest in our 115 release. So we introduced a new variable importance measurement called impurity variable importance, which calculates how purely a node can separate classes from different variables. So the smaller the impurity variable importance it is, the purely the node. The classes are separated by features. For decision tree, this variable importance is calculated by default. So when every time you call tree train, it will calculate and the result will be saved in the result table. And for random forest, for performance consideration, you have to set a flag importance equal to true so that this impurity variable importance can be calculated. At the same time, we introduce a helper function called getVarImportance to make it easier for you to map the feature name and the corresponds impurity var importance. And also this helper function rescales the importance values to represent them as percentage. So they end up sum up to 100 to make it easier to compare between features. Now I'm going to show more details. In this IPython notebook, it's connect to my local Postgres instance, and I just got MADlib 115 installed. I'm going to show the decision tree first. Firstly, I will load a data set called dtgolf, which has a couple of rows for train. And now I call MADlib tree train and use this dtgolf as an input. So the train is down, and from the train output table, I select a couple of columns. And from here, we can see this is the new columns we introduced, which is the impurity var importance. And we can see the importance score are saved in an array. And the order of those scores corresponds to a column in the summary table. I can show it here, the independent var names. So here, if the order in this column is outlook, windy, and temperature, then those three scores corresponds to those three variables in the same order. As I mentioned, to make this mapping easier, we provide this helper function. So if I call this MADlib getVarImportance and use a train output table as an input, we will have the one-on-one map. So now it's easier for me to look at the corresponds importance score for each feature. And also, as I mentioned, this one is slightly different from the number in the output table because we scale them from 0 to 100. This is for decision tree. And similarly, we apply the same concept to random forest. So in random forest, because each tree we already got the impurity variable score, so what we did for random forest is we calculated the average of all the trees to get the average score of each feature in each tree. Here is an example for random forest. I will load another table called rfgolf and use this table as an input table to call MADlib.forest train. Also, as I mentioned, for random forest, you have to specify this flag, this importance flag as true to enable the calculation of importance score. So I'm going to train it, and from the output group table, we will see there's a column impurity var importance, and similarly it will save the scores in an array. Here also notice there is another column called OOB var importance, which is actually what we already implemented before. We call it importance, and now since we introduced another importance score, so we rename this column to OOB var importance, which represents to out-of-bag variable importance. So users can know the difference of those importance scores. Similarly, in the train output summary table, there is a column called independent var names, which has the order of the features. and the importance scores are correspond to the same order in this column. And similarly, you can call the getVarImportance helper function to map them. So now if I call this and use the train output table as input, I will see a mapping between the feature name and both the OOB varImportance and the impurity varImportance. And similarly, they are scaled to from 0 to 100 and sum up to 100. That's all from the new features we introduced to decision tree and random forest. And the rest of the new feature, I will hand it over to Frank.
Okay, thanks, Jingyi. So I'll share my screen again. All right. So the demos that Jingyi just did, as well as the ones that I'm going to do, are posted in this GitHub repo on MADlib's site. So you can go there and look at the demo that Jingyi just did, as well as many other demos for MADlib in the form of primarily Jupyter notebooks, although there may be one or two Apache Zeppelin notebooks as well. So let's look at column vector operations. So we've added 3 column vector operations. The first call is called calls to vec, which is converting feature columns in a table into an array in a single column. Then vector to columns is kind of the reverse of that, wherein it takes a feature array in a single column and then maps it into multiple columns. And then drop columns is a simple feature to essentially create a new table with a subset of the columns from the source table. So let's do a demo of those quickly. So let's start with columns to vec. So I'm going to load a similar data set that Jingyi was using, which has a number of columns here. So now what I would like to do is, so this is calls to vec, right? So what I would like to do then is take the temperature and humidity columns and create a vector from them. So you can see if I run that, then I end up with a feature vector here, which is the temperature and humidity values. Sometimes it's, and I've decided to keep a couple of columns from my source table here, the ID and Outlook columns. Sometimes it's useful to keep all of the columns in the table. So what I've done here is I've specified an asterisk here, so which means I'm going to keep all of the columns from the table. So you can see that I have essentially I have the feature vector on the right-hand side of this table, but I have the rest of the table as originally loaded from the source here. So now let's look at the reverse, which is vectors to columns. So let's load a sample data set. Now you can see I have, for clouds and air quality column, I have a vector with 2 elements from it. What I want to do is split that into columns. So I specify the columns with the array entry to split, and then I give optionally the name of the new columns. So if I do that, you can see that, again, I've capped a couple of columns from my original table. I've split that feature vector into 2 columns called clouds and air quality, right? You can also auto-generate feature names. So if I do the same thing without actually specifying the names of the columns, then it will just call them feature 1 and feature 2, F1 and F2. It's essentially the same operation with auto-generation of column names. So the final one is a simple drop columns table. So here I'm using the source table, and then I'm going to specify some drop columns. I'm going to drop Outlook, temperature, and humidity. So you can see that those columns don't appear in the output. So these are fairly, basic operations, but commonly done by data scientists. So these helper functions have been added there. So let's go back now and look at momentum methods. So a classic fully connected neural network is called a multi-layer perceptron, which was introduced in MADlib last year at some point. So we've made some changes in that we've added momentum methods for MLP. There's two optimizer values that have been added. One's called momentum and one is called Nesterov. And there's some references here which are kind of instructive in understanding the idea behind momentum, and in particular Nesterov momentum. So I refer you to those, but just kind of by way of introduction, maybe I'll show here. So the idea behind momentum is it's kind of a velocity thing. So you can imagine a ball which is rolling down some surface here. And as the surface changes slope, or the gradient changes, the ball doesn't instantaneously go in the direction of the slope change of the slope. It carries a velocity with it, a momentum with it. So if the slope changes, then it will change over time in the direction of that slope, right? In control theory speak, you'd say it's kind of a low-pass filter on the direction of the ball rolling down this slope. So that's the intuition behind momentum. The advantage is that it is a more, for many data sets, has better convergence behavior than MLP without momentum. So Nesterov in particular is based on work that was done by Nesterov on optimizing convex functions. So the idea is it has a kind of look-ahead characteristic to it. So you take momentum, but you also look ahead as to where you would be after your next step. So here's a picture of this method. The blue vectors would be the standard momentum, if you're following this ball rolling down the slope idea that we talked about earlier. But what you do with Nesterov is you actually make a jump ahead to the next iteration, and you look at where you would be there and you apply your correction based on that. So the idea is that you kind of look ahead, apply the correction, and then you apply it to the current step. So instead of this first blue vector here, then you end up with your Nesterov vector, which is the green one here. This is just to show that the blue vector and the green vector have both different directions and magnitudes. And the reason this works is there's a detailed proof by this author here, but it's seen to give better performance for a wide variety of convex functions. So we've done a fair amount of testing with that as well, and here's one example of kind of on Rosenbrock is a non-convex function that a lot of people use for testing optimization. And this is a loss on the y-axis, number of iterations on the x-axis. So you can see that if you use regular stochastic gradient descent, then you get this blue line here. If you use momentum, you get a smaller error, but you can see that there's some more oscillations in the loss function. And if you add Nesterov to it, then you get the yellow line. So the yellow line is showing both better convergence behavior as well as less, it's more stable. So, right, so give a quick example of that. So if we look at the, it's a bit kind of hard to see. It's baked into the existing MLP algorithm. So if you look at this example for an MNIST data set, which is a character recognition data set, so this character corresponds to these gray levels in these pixel boxes believe it's 28 by 28. This is a fully connected neural net. And if we load our data, I already have it loaded. We can look at the first three elements. So you can see the character Y of character 5 corresponds to these gray levels, 0 corresponds to these, etc. So I won't use mini batching here, but I will train this model. And I haven't had to specify the momentum values because they're default on. So while this is running here, you can look back and see that, for momentum, the default is 0.9, and NestDraw by default is on, true. So this is running now. It takes should take a few more seconds to run this model. So this is has a single internal, layer with 100 nodes. And you can see it's finished running now. If we look at the first 10 coefficients, we've got these. We can do prediction. So then if we do prediction, running this prediction, and it's showing, let's look at our training accuracy. It's showing a training accuracy of 95%. So that's pretty good. A single neural net, 100 nodes, trains at 95% on the MNest data set. Okay. Let's look ahead now to next releases. So we just did the 115.1 release, or 115 release. 115.1, the primary thing here is Ubuntu support. You can see from this Google Trends chart, as well as from this blog post here, that with respect to Linux distros, Ubuntu is probably the most popular. So we haven't formally supported Ubuntu with Apache MADlib before, but the focus of the 115.1 release is more formal support, and then we'll post the Debian packages on the Apache distribution site after this. There are some other minor bug fixes and such that we're working on, and you can check the JIRAs to see what those are about. So looking a bit further ahead to second half of this year, this is of course subject to community interest and contributions. The things that we're thinking about working on is, since we use semantic versioning, or 2.0 release is an opportunity to clean up the interface because we don't have the restriction of being backward compatible. So we're looking at cleaning up the interface to make it more consistent. And there's a couple of pages on the wiki, and the links will be in this deck when Bob distributes it. You can have a look at and see what the ideas are there behind proposed interface improvements. There's 2 wiki pages that go into some detail around that. On the algorithm side of things, there's kind of 2 main areas of work that we're looking at. Again, you can look at the JIRAs to get some details. But one is a more convenient way to support Python functions. So Python is probably one of the most common languages that data scientists use. And by virtue of the Postgres heritage of Greenplum, we can run PL Python functions. So the idea behind this is to make it much more convenient for data scientists to bring Python code to Postgres or to Greenplum, and then call these generalized fit and predict functions to build models in parallel. So that's one track of work. The second track of work is around larger distributed models. And here's one example that we're thinking about, which is supporting a distributed training of a convolutional neural net. In this case, using Keras with a TensorFlow backend. So this is not parallel models. This is actually merging the models, so building very, very large training models for very, very large data sets. Yes, so that's a look ahead to 115.1 and to 2. Here's a bunch of resources that are available regarding Apache MADlib, including the Jupyter notebooks that we've been showing in this demo. And that's it. I'll turn it back over to you, Bob, to see if there's any questions.
Okay, thank you, Frank. And at this point, I'd like to invite anybody in the audience who has questions to pop them in the chat window or just unmute yourself and go ahead and ask them. Okay, looks like we have no questions. So at this point, I will go ahead and conclude the call. Thank you all for attending.